Okay, today we're going to discuss gravity on Earth. All right, gravity is a pull force, and it is a constant pull force. So something that falls to Earth continually gains speed. It picks up velocity. It keeps speeding up because the force is always there. Okay, we're going to discuss today's gravitational pull on Earth as if we are in a vacuum or where there is no atmosphere or no wind friction stopping an object from falling. So we have to keep that in mind, that when we're talking about the objects falling on Earth right now, we're talking about in respect to there being no atmosphere. So no wind is going to stop it or hold it up from falling any faster towards the Earth. Okay? So here you see Wreck-It Ralph, and I don't know if any of you have seen the movie, but when Fix-It Felix fixes everything, he grabs Wreck-It Ralph, and Wreck-It Ralph gets thrown off the top of the building into a mud puddle. But so when Wreck-It Ralph is falling, or something, if anything, if we have Ralph falling from the roof, and we have a feather that's my drawing of a feather, falling from the roof. They will fall at exactly the same rate. Okay? Every second, they will be picking up more speed. Okay? And they will hit the ground at the same time if we are in a vacuum. Okay? So the acceleration due to gravity here is 9.8 meters per second squared. Some people round that off to 10 meters per second squared, but we're going to keep it at 9.8 for now. So the velocity of Ralph and the feather will fall to the ground, to that mud puddle, at 9.8 meters per second every second. So after 1 second, okay, when Ralph and the feather are falling, they are now moving at 9.8 meters per second. Okay? That's 1 second. 1 second later, so the second, at second number 2, at 2 seconds, they will be falling at 19.6 meters per second. That is their velocity. Remember, that is their velocity falling towards the ground. They are accelerating each second at a rate of 9.8 meters per second. Okay, so every second their velocity increases 9.8 meters per second. So at the third second, Ralph and the feather will both be falling at 29.4 meters per second. Okay, and we know this is velocity because of the units we're using, meters per second. And at the fourth second, as they crash into that mud puddle, get ready for the next game, okay, they're moving at 39.2 meters per second. Okay? So the force of gravity on an object on Earth can be calculated by using Newton's second law. What we're saying here is force equals mass times acceleration. Now, acceleration due to gravity on Earth, if we're talking about acceleration due to gravity, we're talking about whatever the object's mass is times, just do it like this, times 9.8 meters per second squared. And that equals the force. So if you wanted to find out the force at which Ralph hits the ground versus where the feather hits the ground, all you'd have to do is calculate his mass. So if Ralph's mass is 1,000 kilograms, okay, you would plug that in here, okay, and you would find that 1,000 times 9.8 meters per second squared, Ralph is hitting the ground with 9,800 newtons of force. Okay, and if the feather weighs 1 kilogram, let's say, all right, because the feather's not going to weigh 10 kilograms. If a feather weighs 10 kilograms, or 1 kilogram, excuse me, it's hitting the ground with a force of 9.8 newtons. Okay? So gravity on Earth. Falling objects have the same acceleration. Okay? All falling objects have the same acceleration because gravity pulls it to the Earth at a rate of 9.8 meters per second squared. Okay? The reason things may fall slower or faster on Earth as we know it is because there is an atmosphere. There is air resistance, or air friction, if you will. Okay, which may prevent objects from falling at the same rate. In theory, gravity on Earth without air friction, so in a vacuum, whenever you see that on a test, it says in a vacuum or on the moon, or in space, they're trying to tell you that there's no atmosphere. No atmosphere, which means no air friction to slow the acceleration. Okay? So objects with different masses on Earth fall at the same acceleration. Now, building on that, well, what does that mean? How does that tie into this next statement that says objects that are thrown horizontally fall at the same rate as one that is dropped? Let's say you're standing on top of that building with Fix-It Felix and all his friends. Okay? And you walk to the edge, and there's two of you standing there. And one of you throws a baseball horizontally, straight out horizontally. Okay? And the other one of you drops the baseball at the same time from the same height. Okay? Those objects will hit the ground at exactly the same time. Okay? So whether or not it's thrown horizontally, which means out, or dropped, those objects will hit the Earth at the same time because gravity, even though it's going horizontally, it's still pulling it down at the same rate as if it were pulling it straight down. Okay? Let's give another example of that. If we had a cannon, okay, and this is my terrible rendition of a cannon. Okay, and if that cannon shoots a cannonball straight out, okay, and a cannonball from the back just fell straight down. The cannonball that fell or was dropped before putting it in the cannon would hit the ground at exactly the same time as the cannonball hit the ground out here. Okay? What we're saying is, look, even though there's a horizontal push force pushing it this way, gravitational pull is pulling it down at exactly the same rate as something that would be dropped directly down. Okay? So, let's try and draw that a little bit more efficiently. Okay? We have our cannon, our fuse, right? Cannonball shoots out. As soon as that cannonball shoots out of the cannon, it starts to drop towards the Earth. Okay? So as soon as it shoots out, it starts falling. Okay? So if you were standing here, holding a cannonball at the same height, and you dropped it at exactly the same time that cannonball is shot out of the cannon, both of them hit the ground at the same time. Okay? The reason it doesn't hit the ground right below it is because you've put a horizontal force behind it as well. So like missiles and bullets and cannonballs, and if you throw a baseball, the faster you can throw something, the longer it will take to hit the ground. It will cover more distance in that time it takes for it to drop. So in order to cover more distance, it has to move at a faster velocity away from the cannon. Okay? So remember, gravity is a pull force that pulls everything to the ground equally. All right? So if we want to calculate the force of an object that is falling due to gravity, okay, if we had, let's say this cannonball weighed 50 kilograms, okay, it falls to the earth. That 50 kilogram cannonball falls to the earth, like we said, at a rate of 9.8 meters per second squared. Remember, this is the same thing as Newton's second law. Force equals mass times acceleration. But in this case, we know that the constant of acceleration due to gravity is going to be 9.8 meters per second squared. Okay? So when we run the calculations, we do 50 times 9.8 meters per second squared, and that gives us a force of 490 newtons.